Okay, and you may as well open up R as well. Can't get to my folder here. There it is. That's how you do that. Okay. So open up R as well. By the way, I didn't introduce you to something called R Studio, which is a nice way to use R. You can just download it, and then it's basically like this, but it has 4 panels, and like one of them is this panel, and then the other one just makes it more convenient. Like you can do other things while you're doing this. So maybe we'll do that, but I haven't had time to do it. But I recommend it. It's more convenient than this particular interface here. It's called R Studio. It's one word. Okay. So let's take a look at this, what we've done up to now. So we were talking about the bobbleheads, and we're trying to decide whether they're going to be effective in terms of promotions and how effective they're going to be. We'd like to get an actual number for the value of the bobbleheads in terms of how many people they, on average, will bring to a game. Okay, so we want to go in that direction. And just to review, I reviewed this at the beginning of last class as well. The table function, right? Maybe the third time that we do it, it might sink in. So what does the table function do? Like in this case, what is this going to do? Remember, it's going to print out a table of this variable versus this variable, and then that each cell of that table is going to be the counts. So I thought that this would be, a better name for this would be count, right? Rather than table. Table's not really, it's not very good. I think it's maybe something to do with counts would be a better name for that function. But what will it tell us? It tells us this, and we saw that already. Okay, and then we also built this graph. This graph here, this one. And I think we ended when we were discussing this graph. Or what does this graph tell us, if anything? Anybody able to get any information out of this graph?
So there are more fireworks
All right, okay, that was good, yeah. There's more fireworks on clear nights rather than cloudy nights, which that makes sense, I guess, except that, yeah. Anything else? Anything else this table tells us? How about this one here? This panel here. Does that tell you anything? What's the x-axis? Temperature. And what's the y-axis? Attendance. Does this tell you anything? First of all, there's no fireworks there, but why is that, by the way? This is clear daytime, right? They don't have fireworks during the day. Okay, but, so there's no fireworks, but what else does it tell you? Well, I mean, it's not very clear, but I mean, it's not very exact, but there is a downward trend here, right? Kind of. It's not very strong, but there's a downward trend. So what does the downward trend mean?
the higher the temperature is,
Yeah, the hotter it is, the less people are coming. But that's specifically for day games, right? But that's not really true for night games, is it? Of course, yeah, right, it's not really true for night games, and it's not really true for night cloudy games, night clear games. And here there's no pattern because there's only one dot, so that's can't see a pattern there. Right? Everyone agree with that? Anything else you can see here? I saw this, but I don't know how to say anything about that. Does that mean anything? Doesn't really mean anything. Oh, yeah, it does mean something. So what does this mean? The red triangles here. There's an increasing pattern here as well, right? So what does it mean? How do we interpret that? How do we state that? This is the temperature, this is attendance, and we're only talking about what? Fireworks days. So what do we say? As the temperature increases, on a cloudy night, when they have fireworks, attendance increases. I don't know, that doesn't ring a big bell in my head. Doesn't really give me, I think there's too many things I'm saying there. It doesn't really, it's a little bit hard to make any intuitive sense out of it. But anyway, there is this pattern of what? As the temperature increases, the attendance increases, right? But that's only for fireworks nights in this kind of environment. Okay, it's a little too many things to juggle in your brain, but you could say that, right? Okay, so everybody get that? Okay, so this is the code that was used, and what's the name of the package that's being used in this code to get this kind of fancy graphics? What's the name of the package? Lattice, right? So you'd have to download Lattice, and then you'd have to store it in the library or bring it into memory. And then you can use, for example, this XY plot down here. Okay? Excuse me for a second. So, everybody follow? So let's not go through all of this. It's fairly complicated, and to get that graph to work, you'd have to work. This takes practice, right? You'd have to work with this again and again and again before you're going to get good at R, right? And the only way to do it is maybe follow somebody's examples and just or look at the documentation and just keep trying things, and eventually you'll get what you want, and then you'll get used to it. Okay, so attendance by opponent. Okay, this graph is also, so we can generate this graph again. I mean, we did this last time. What's the x-axis here? Attendance, and the y-axis are the different opponents, different other opposing teams. So is there any conclusions we can derive from this picture?
There are more attendance at the night game.
Really? You can see that? Oh, you mean here? Oh, right. Okay, yeah, I think that sounds right. First of all, there are more night games, aren't there?
Yeah.
There are more night games. And there are more, but probably even percentage-wise, there's more attendance at night games than there are in day games, even percentage-wise. Anything else? Well, I mean, we can see like they didn't play the pirates very many times. I don't know why that is. I thought they were supposed to play each team the same number of times. But it doesn't look like that, right? They only played the pirates 3 times. And they only played this team, the Reds, 3 times. But this team, they played a lot. I wonder when that is. Anyway, anything else? Maybe they look at the angels compared to the I don't know. Okay, how about the angels compared to the Marlins? Angels compared to the Marlins. Can you say anything? Generally more higher attendance for the Angels than for the Marlins. And how about this one? This is kind of weird. The Pirates, they had 2 games with really low attendance and 1 game with super high attendance. I wonder if that was the first game. That could have been the first game of the season. Remember, we said that there were 2 games where they had 56,000 full attendance, 56,000. So maybe this was the first game. Or the Giants could have also been the first game. So one of these 2, either the Pirates or the Giants, is kind of draws a lot of people, right? I don't know which one is the first game. So if it was that one, I won't make that statement about. But the other one draws high attendance, right? For sure. Okay, and so on. So we can make this, and let's see, what did they use here? They used something called a BW plot, but that one, I don't think we see that one. And then they used some fairly complicated stuff here, we haven't really talked about, where we define a function, and then they use it. So we have to go through that kind of R code, which we haven't done yet. All right, so now let's get into the data mining part, and let's do some modeling. So in order to do data mining, the traditional, or I don't know if it's traditional, but the general framework for doing data mining is to take your entire set of data and split it into 2 parts. So let's say we had, how many games were there altogether? Does anybody remember? I don't remember. Well, in other words, what I'm asking basically is how many dots are there here? Because each dot is a game, right? So how many dots are there? So does anybody remember how many games there were?
1.
What? 81. Oh, thank you, that's right. So there are 81 games, right? So what we want to do is so suppose this represents the entire set of games. So here's a game 1, game 2, game 3, game 4, game 60, game 68, game 81, and so on, right? That's the entire set of games, okay? And what we want to do is randomly select a set of, say, 50 games, and call that, so let's say we do this set, and we call that the training set. And then we're going to take the rest of them and call that the testing set. Okay, so everyone get this idea? We're going to split it into a training set and a testing set. So, as I said, like in Weka, which is the way we do data mining in our data mining class, that's very simple to do. You just click a button and it does it for you. But it doesn't work, we don't have that facility in ours, so we have to do it ourselves. We have to somehow split the data into two sets and call one set the training set and the other set the testing set. So we have to split the data into a training set and a testing set. So if we look at n row for Dodgers, we get this. And that tells us what? The number of rows in our data frame, meaning the number of games, right? Each row is a game. Okay? Now here's a function called repeat. So what does this do? What do you think this does? It repeats whatever you put in the first argument this many times. Okay, is everyone follow that? Repeats whatever you could put A here, and it would give you 10 A's. Or you could put A 15 here, and it would give you 15 A's. So try that yourself in R. So try the rep function, the repetition function yourself. But if you put in A, I'm pretty sure you have to put in A with quotation marks around it. Although I'm not sure, is that true or not? When you try it with A, don't you need quotation marks around it? Does it work? Okay, so does everyone get what the rep function does? Okay. Okay, now there's another function called trunk, and that's like floor, but we haven't used, I don't know if we used floor either, but for negative numbers it rounds towards 0. So try floor on the number 3.8. So put floor, open bracket, 3.8, close bracket. What do you get? 3, right? Okay, try floor on 3.4. What do you get? Okay? So what does it do? It just finds the lowest, the lowest integer value, right? So if it, the closest integer that is less than the number that's there. Okay? All right, now try floor on, not closest, I said the wrong thing, the low, on the low side. It has to be on the lower side. Now try floor on negative 3.8. What do you get? Floor on negative 3.8. What do you get? Negative 4, right? Does everyone get it? Everyone got negative 4? Okay, try floor on negative 3.2. What do you get? What do you get? Negative 4 again. Okay, now try trunk on 3.8. Trunk on 3.8. What do you get? On positive 3.8. Try trunk on 3.8. What do you get? 3, right? Now try trunk on 3.3. What do you get? 3. So this is not rounding, right? This is not what we call rounding. Rounding 3.8 would give you what? 4. But 3.3 would give you what? 3, right? So it's not rounding, it's just bringing it down to the lowest, the closest integer that's less than that number. Right? Everyone get it? Okay, but now try trunk on negative 3.8. What do you get? Trunk on negative 3.8, what do you get? You get negative 3, right? So it's bringing it towards 0. Okay, so the direction for trunk is towards 0. The direction for floor is lower than. Okay? Does that get everyone understand? So we have those functions. Okay, so trunk 5.6 is 5, trunk negative 5.6 is negative 5. Floor 5.6 is 5, but floor negative 5.6 is negative 6, right? Okay. So what what are we doing in the first line of this code here on the bottom? So if you want to understand code, you have to work from the inside out. You have to look at it from the inside out. So first of all, what's here? What's n-row Dodgers? Well, we did that up here, right? N-row Dodgers is what? 81. We're going to multiply it 81 times something, right? Times what? Times 2/3. So what is that? 2/3 of 81 is what? Is it exactly 54? Okay, so in that case we wouldn't need trunk because it's exactly 54. But if it was 54.3, what would trunk do? It would make it 54, right? Okay, so in this case we don't really need it, but just in case, right? In general, we could use the trunk function. Okay, now also we could also use the floor function because we're never going to have negative number here anyway, right? So it's not going to really make any difference. But he uses trunk for some reason. Okay? For no reason, I should say. Okay? Is that clear so far? So what is length equal? 54. Okay, now do this. This part is what? We just did that part. It's 54. And n row of Dodgers is what? 81. So 81 minus 54 is what? 27. So we have a number here, 54, which is what? 2/3 of the data set. And we have a number 27, which is what? The remaining third, right? Okay, does everyone understand this code? Okay. So now what does this do? So it's rep 1, and then how many times are we going to print 1? 54, right? Does everyone agree with this? Everybody understand, by the way, what this number is, 39? That means that this is the 39th element in the vector. So this is the 40th element in the vector. So this is the 50th element in the vector, and so on. Okay, everyone clear on this so far? Okay. And of course this is just doing the same thing, but with, sorry. So how many 2's are going to be here? 81, right? 81 2's, right? Okay. What we want is a random selection of the Dodgers data set, right? Because we want to take a random selection and put it into our training set. So we're going to create what we call a training set, or I should say we're going to create I think this is just a vector, right? So what is this vector going to contain? So here's C, so it's a vector. So what's this first part? So we're going to get a bunch of 1's, right? How many 1's? I think it goes to here. How many 1's are we going to get? 54. And then comma, we're going to add into this vector. What's this going to give me? A bunch of 2's, right? How many 2's? We did this one. Length is what? What was it? 27, right? It was 27. Right, so what are we going to get when we do this? 54 1's and 27 2's following it, right? Everyone agree with that? Okay, what will be stored in training test? We just said that. This. Right, everyone agree with that? Okay. Now, let's introduce another function called the sample function. Okay, if we sample, what is this 1:10? What is that? It's a vector, right? It's a vector of how many elements? 10 elements, right? From 1 to 10, right? if you do sample on a vector, usually sample will take 2 arguments. But here, how many arguments is sample taking? Just 1 argument. So in that case, it does something special. But otherwise, if I wrote sample 1, okay, try this. Try sample 1:10, full colon 10, comma 3. What do you get? Sample 1, full colon 10, comma 3. What do you get?
5, 2, 3.
He got 5, 2, 3. Anybody get something different? Sample 1, full colon 10, comma 3. What do you get? Anybody get anything different? Somebody's using this. That's good. Here, I mean, if you don't mind, I'm going to show your screen. This is RStudio. Okay, so it has the regular panel down here that we're working in, but it also has some other stuff just for convenience. Like when you want to see help, it shows up here. And if you want to see the data set, it can show here. Okay, so that's RStudio. Okay, anyway, anybody get anything different for sample? I assume you did. So if you do sample a vector, comma, a number, it'll take a random sample from this vector and with the number as the number of elements, and that's random sample. If you don't use a second argument here, then what it does is it just takes a random permutation of these numbers. Okay, a random permutation of these numbers. So 1 is here, 2 is also here, 3 is here, 4 is here, 5 is here. All the numbers are here, but it's just been mixed up. Okay, so it's called a random permutation. Or it's just called a permutation, not a random permutation. It's called a permutation of this vector. Okay, a permutation is just a rearrangement of the vector, of the elements in the vector. Okay, so anybody guess what we're going to do next?
Sample training test.
We're going to sample the training test. And what's that going to give me? A random sample of it's going to give me a permutation of the training test, right? Data. So we're going to get 1s and 2s and 1s and 2s and so on. Okay, so let's do that. So we do that, and we'll call it Dodger's $score training test. And this is now a permutation or random arrangement of these numbers, right? Everyone agree? This will randomly assign 54 rows to group 1, training set, and 20 knowable. That's not true. Doesn't do that. Anyway, let's see what he does next. Oh, okay. All right, anyway, everyone agree with this code here? I'm not sure. This doesn't really make sense, but this makes sense, right? Okay. Now, what's he do next? He takes the Dodger's training test and does what to it? So it's the same thing that we have here. It's this thing here, this thing here. So it's this vector here. And what does he do with it here? He puts it into this function, right? So what does that do to it? Makes it into a factor, right? So that's just a conversion that allows us to then utilize other functions that we wouldn't be able to use if we didn't turn it into a factor. Otherwise, it's still the same. Okay, so it's a factor. We specify the levels as 1 and 2. Does anybody remember what that does? That's like for ordering. That says that 1 comes before 2. Well, you would normally think that 1 comes before 2, but it doesn't when it's a factor. Okay? In fact, what would the, yeah. So, but if you specify this like that, then you're specifying that yes, 1 does come before 2, because once you turn it into a factor, these are not numbers anymore. These are just arbitrary symbols. Okay? But now we're turning it into a factor, but we're also saying that there's an order. And then the label is train for 1 and test for 2. Okay? All right. Now, this is a very important function. This is one of the most important functions in R, one of the most useful functions in R, I should say. Okay? The subset function. So subset is one of our most important functions. So here we have and this is a kind of a big subject. So I kind of take my time explaining this. So first of all, we have a vector from 1 to 10, and we give it the name x, right? Everyone see that? Now, this symbol here is called what? What is that symbol called? Okay, we often call it less than. And what kind of thing is it? It's called an operator. Okay, it's called an operator because operators are just something where you have this is called a binary operator. Binary operator just means you can have something on one side and something on the other. So like plus is a binary operator because I can say 8 plus 1. Right? So that's called a binary operator. This is also a binary operator, but the result of this operator is going to be either true or false, so we call it a Boolean operator. Okay? So x is less than 4. Now x happens to be a vector, so the answer is going to be a Boolean vector. Okay? So what is this first one? Why does this first one say? Try this yourself, first of all. Try it yourself. See? And try it with 9. X is less than 9. Let's see what you get. So what do you get when you do that? You get false, 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 false. Up to the last 2 are true, right? Okay, so what is this doing? It's just saying that, which of these, so the first one, the first element of x is 1, is that less than 4? Yes. Is 2 less than 4? Yes. Is 3f less than 4? Yes. Is 4 less than 4? No. No, 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 no. Okay, is this clear? So because x is a vector, it's going to do this evaluation for each element of x. Okay, is that clear? Okay, now how about this one? Now, why do we need a double equal sign here? Because if I used a single equal sign, that's the assignment operator. And I don't want to do that now. I don't want to assign 2 to every element of x. This is different. This is asking a question, just like this was asking a question. This is an operator. This is a Boolean operator. And what's the question that this is asking? Is x equal to 2? So what's the answer? Only in the second case is it true, right? Is that clear? Okay, how about this one? Okay, this is the OR operator, O-R, OR. Now, I'm going to do this on the board. I don't like to do things on the board because you can't see them in the recording, but you can look this up for those of you who are only listening to the recording. That is not you guys in the class. But you can look this up in somewhere on the internet. And I want to talk about these 3 logical operators. I think this is, so this one, or, So if I have two statements, let's say P is today is Thursday, and Q is it is snowing today. Okay, I have those two. And if I, so first of all, is it true that today is Thursday? Yes. Is it true that today is snowing? No. So one of those is true and one of those is false. Now, suppose I want to make, but it's possible if I make this discussion tomorrow, this will be what? P will be true or false? This will be false. It's possible that this could be true or false, right? So in other words, P can be true or false. There's two possible values, and Q can be true or false, two possible values, right? Okay? So if I want to consider all possibilities, I'll put P and Q. So first of all, both of them could be true, right? That's one possibility. So I could have true and true, right? Or I could have true for P and false for Q, right? Or I could have what? False and true, or I could have false and false, and those are the only four possibilities, right? This is different than numbers. Like if I gave you number X and Y are numbers, then how many different possibilities can we have for X? Generally speaking, like let's say X and Y are real numbers. So X has how many possibilities? Infinite number. And Y has how many possibilities? An infinite number. So the combination also is infinite, right? But here, P and Q can only take on two values, either true or false. So together, they can take on four possible sets of values, right? Does everyone agree? Okay, so if I say P or Q, okay, and so what does that mean? So let's suppose that this is P and this is Q, and let's suppose that this, yeah. So if I say P or Q, what does that mean? Well, I'm sorry, let's do first the easier one maybe, is and. Okay, P and Q. Okay, so what does that mean? Today is Thursday and it is snowing today. So, if it happens to be that both of them are true, that is, it happens to be a Thursday and it happens to be snowing, then what would you say about this statement? You would say it's true, right? On the other hand, if it happens to be true that P is, that today is Thursday, but it's not snowing, what would you say if I said, today is Thursday and it's snowing? You'd say, I didn't say something correct, right? It was false. And how about if it was this combination? It's not really Thursday, but it is snowing. What would you say if I made this statement? False. And how about this one? False. Okay? So this is called the truth table for the AND operator. Truth table for AND operator. Okay? Now I want you, on your piece of paper, to make the truth table for the OR operator. So do it on a piece of paper. Tell me what you get. So in other words, I wanted you to do this. So do that. Make the truth table for that. So again, for P and Q, each one can be what? Has two possibilities. So together they have how many possibilities? Again, just like before, they have four possibilities. So go ahead and make the truth table for this on a piece of paper. Or if you don't have a piece of paper, you can use your hand. You can write the truth. You can use your hand. You can put it on your hand so you don't forget it. The whole day, you'll remember what the truth table is. What does it look like? And this is not English dependent, right? This is logic dependent, right? It's not, right? It's not just true in English, right? Except, oh, I'm sorry. It is just true in English. Because in English, the word or has a kind of fuzzy meaning. So actually do it in your own language. That's what I want you to do, sorry. Do it for the word or, whatever the word or is in your own language, and do the truth table. Because actually English is English dependent. It is because English actually has a fuzzy meaning for the word or, not a clear meaning for the word or actually. So try it in your own language and tell me what you get. If both of them are true, that means today is Thursday and it's snowing, and I say today is Thursday or it's snowing, you wouldn't say I was lying, right? So how about the next one? If it's, if today is Thursday but it's not snowing, and I say today is Thursday or it's snowing, would you call me a liar? Today is Today is Thursday or it's snowing. Can you accuse me of lying? No, because I said or. It's like if I have a child and I tell him, you can go to the amusement park or you can go to the movies. And he does both. Is he cheating? No. Or if he does one of them, is he cheating? No. Okay? Maybe that's not such a good example, but anyway. So the only time that you would accuse somebody of lying is if both of the P parts are false and they say P or Q, right? Now actually in English, as I said, the word or is kind of fuzzy because if I say to my child, you can go to the amusement park or you can go to the movies, and my child goes to both, is that okay or not? You might say no, and you might say yes, but the word or in English isn't clear about that. So if, oh sorry, yeah, that's right. So but we are talking about this one. So the only one that's false is here, okay? So that is the or, that's the way or works. Actually, I won't do not, but everybody knows what not. And instead of the word or, in R they use that symbol. Okay? And instead of the word and, in R, I think it's this. Maybe I'm wrong. I think that's a or. That's and. Okay? So, now you understand the or operator. Now, let's take a look at this. So what is this going to do? What is this going to do? This one here. So x is less than 3. What does that look like? It's going to be true, true, false, 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 right? And this one, what does this look like? So let's write it here. The first, we're going to have two statements. X is less than 3, or x is greater than 7, right? Okay, so what about the first one? X is less than 3. What's that look like? That's true, true, false, 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 right? Okay, what about the other statement, which is x is greater than 7? What's that look like? It's going to be false, false, true, true. And just true, true, right?
No.
Right.
True. 8 is 19.
Oh, sorry. Right, true. Okay, so now what? we're using the OR operator. Now the OR operator is what? The only time that it's false is when? When both of the pieces are false, right? So, how about here? Are there any times when both of the pieces are false? How about this one, the third one? What was that? That's x is greater than, I'm sorry, that's 3 is less than 3, that's false, and 3 is greater than 7, that's false. So that's going to give me a what? A false. But how about down at the last one? What's that going to give me? False and true. False or true is what? False or true. False or true is what? True. Okay? So that we're going to get a pattern of true, true, false, 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 true, 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 right? Okay, does everyone understand that? Okay. Let's keep going. Okay, by the way, in R, there's a variable called letters, and it just gives you this whole, it's a vector with these elements in it. Okay? So you can assign letters to y, print out y, and you'll see these letters. Okay? Like that. Okay, so let's try this. Y equals c. Is y equal to c? That's the equals operator. What's the result going to be? It's just going to have one true element, right? And the rest are going to be false. Everyone agree with that? Okay, try that yourself. Try that one yourself. Set letters equal to y, and then check y equals double equals c. Okay, we just did that. Okay, how about this? Z is from 27 to 52. The length of z is what? Okay, that makes sense, right? It's just the length of the vector, right? That's the length function for a vector. Z is less than 30. What's that going to give me? It's going to give me true, 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 true. 4 truths? Great. 27, 20, 29. Right, 3 truths, sorry. But true, 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 and the rest are false, right? Okay. Okay, now, subset y, z, less than 30. Okay, let's, first of all, what is y again? Sorry, doesn't make sense. Oh, yes, it does. Okay, what is y? This is y, so it's the letters, right? Everyone follow this? And what is this? Z less than 30? We just did it. Z less than 30 is here, right? How many elements are in this vector z? I'm sorry. First of all, how many elements are in z? 26. That's the same number of elements as what? In the alphabet, right? Okay, I did that on purpose. And how about z less than 30? First of all, is it going to be a numeric? Is this going to produce a numeric vector? Is this going to produce a character vector? Is it going to produce a Boolean vector? This is producing a Boolean vector, right? This is a Boolean vector, right? A logical vector, right? Okay, everyone agree? It's a logical vector. It's not numbers, it's not strings. Okay. So you understand the two arguments that I'm putting into this new function called subset, right? Which we haven't done. We haven't looked at this function called subset, but you should understand the two arguments. Is it clear? The two arguments that I'm putting in? Okay. So what's it going to do? Well, you don't know what it's going to do because we haven't covered it, but anybody want to guess what it's going to do? So what's the right-hand argument going to give it? What's the right-hand argument look like? It's this vector here, which consists of what? 3 truths and the rest are false. And what's the left-hand argument here? It's just the letters in the alphabet. So what might this do? Any guesses? No guesses?
IDC.
Any guesses? Okay, well, we don't know. So let's see. What's it doing? First of all, I can say it's selecting. It's selecting. It's choosing a subset of the first argument. The first argument is what? All the letters, and it's going to choose a subset. Which subset? The one where the second argument is true. Okay? Does this make sense? Okay? It's a very useful function. And what's this going to do? Training test. We've gone sort of far away from training test, so we don't remember what that is, right? What is it? First of all, let's go back and see it. It's a factor. Here. Training test is a factor, right? But it came from where? It came from, where was it? This. Came from this. So it was this, we have this, and then we did what? We did sample on it, so we got a random ordering of this vector, right? You guys ever remember that? And then we turned it into a factor, but that's not so important right now. Okay? So, everyone see what it is though? It's a random ordering of this vector. Okay, now what do we do with it? That. So this part here, just this part here, not equals train, but just this part here is what? A random ordering of that, of that vector, right? Of 1s and 2s. But remember, when we turned it into a factor, we gave it labels, right? We called it, what did we call it? Train and test. So what is this doing? No. So what's this, just this part here? Just this part here, what is this? It's a Boolean vector. Some of them are equal to true, and some of them are equal to false, right? Right? Everyone agree? So we have basically a so which ones are going to be true? The ones where we had, what was train was 1. So it's where we had the 1s in that permutation vector, right? So it's going to be here, going back to here. It's going to be, I know this is a little bit tedious, but it's good. The ones that are going to be true, this is 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 going to be false, 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 true, right? Understand? So some of them, we're going to have a vector that has some true and some false. And we're going to put that into the subset function. So what's going to happen? Remember, the subset function only selects from here the ones where this is true. Right? Does that make sense? So we're going to get only, how many elements from Dodgers are we going to select? 54 random elements from Dodgers. Okay, does this make sense? So we had to do all of this just to get a random selection of elements from Dodgers. Okay? So it's a lot of work to do, but that's the way he's doing it in this text. Okay? Everyone follow it? Okay, so when we do this, and we call it Dodgers train, first of all, if we check what kind of object it is, we check the structure of Dodgers train, we see that what kind of object is it? It's a data frame, and it has all the variables in it that we had before, all the columns that we had before. But how many are there? 54, right? There are 54. Okay, so this is a random selection of 54 out of the 81. So that seems like an awful lot of work to do. But that's because we had to learn a lot in the process, right? We had to learn what the subset function was. We had to learn about and then or, and so on, right? So we actually did a lot of stuff that wasn't really related to what we were trying to do, but we needed it. So that's why it was a lot. Okay, so what about training test? I'm sorry, what is in training test time? Oops. Okay. All right, so now let's go and look at the code that we have and see what he does. So open up your code. This is, I think, chapter 3, right? And take a look at the code. And in fact, I'll put it in my documents folder. Oh, it's not chapter 3, it's chapter 2. Sorry. What happened to my... There it is. Okay, so let's look at program. So what row are we at in the program? Okay, so where are we? What line are we at now? Which one? 93. Right. Okay, 95 does what? What does 95 do? It does exactly the same thing, but to create our testing set. Okay, so we have Dodgers train and Dodgers test. Okay, then we use the LM function. Now, I think we used this very briefly in the past. Anybody know what LM stands for? This is for doing regression. Anybody know what LM stands for, though?
Linear model.
Linear model. Okay, regression is referred to as linear model in R. Okay? One thing is, where is my model? Where is that? I don't see that here. Oh, sorry. That's going to be the name of it. And so let's try, let me put this in. Do we have, sorry, here it is. Okay, so here he did this. So he's saying that the model is that we're going to try to predict attendance, and the variables that we're going to include in our model are ordered month, so the month, the day of the week, and the bobbleheads. Okay, so that's the way to specify the model. Notice these brackets here. Okay, so what the model that we're trying to test is, we're trying to predict this variable, and we want to consider using this variable, and this variable. Now you may want to test a different model, okay? But in this example, he's just going to, by testing a different model, I mean use different variables in here, right? You might not want to use ordered month. You might want to use one of the other variables, okay? But here he's using this one, and this one. So what do you think? What about, why is he using month? In other words, he thinks that month is a factor in what the attendance is going to be. Okay, why is he using this? Do you agree with that? That the day of the week might be a factor? Yeah, maybe Friday nights people are doing other things so they don't go to the game or something like that, right? And then, of course, the main thing is we wanted to test bobbleheads. Okay? So we're gonna include that as well. You could include other variables as well, but this is the model that he's going to test. And the way that you structure this so that you can put it into the LM function is like this. So you say the variable you're trying to predict, you put the tilde, you put the variables that you want separated by the plus sign, and you enclose that in these kinds of brackets. And then you can assign that to a variable, and you can put that in here. Okay? And then you have to specify, of course, where your data is. And our data for the first try at this is our training data. Okay? So let's try to do up to here. I'm going to put all of this into R, but this doesn't work, right? I have to load in some libraries. So let me load in some libraries first. So what are the libraries I need? I need Japan. I need... What were the libraries that he's using? I remember he's using Lattice. That. Lattice. What else? What else do we use? Car. What else? Really? I thought there was more. Car and Lattice, that's all? Okay. And now, let's see if this works. Okay. All right, so can run all that code. And now I have a linear model, a regression model, with that we just talked about, and that's stored in here. Okay, so what's next? Oh, sorry, one more thing. He sets a seed here. Oh, I did that, yeah. Okay, so you could do that also. That's kind of setting a seed for I think it's for the using the sample function. It just, if we all set the seed, then we're all going to get the same random sample. If we all set the same seed. Okay? So otherwise you and I would get different ones. So now what? Okay, now we're going to, now we've built this model. What's it called? Train.model.fit, or train.model.fit. And now we're going to make a prediction. So let's test this out. Let's do this. Run that code. Okay. And then let's see what that is. So, what do you think we've done there? How many elements are in this result? How many elements are in the result? So this is the 49th element. So this is 50, 51, 52, 53, 54. Okay, so what's that make you think we've done? Let's try, what was the, let's find, what was that called again? Dodgers, where was that? Train. That was here, right? Yeah, let's try doing this first of all. What's that? Okay, what's this give me? It's going to be the structure of my training set, right? How many elements are there? 54, right? Okay, now suppose I don't want the structure, I want the actual data. So I don't want them. I want to get rid of that. Now if I get the actual data, it's going to be kind of big, right? It's going to be hard to look at, but so it's not very clear. But I specifically want, wait, let me do that again. I specifically want the attendance. Okay, let's try. If I want the attendance, how do I get the attendance in Dodger's train? How do I get the attendance in this, in here, Dodger's train? So I should type Dodger's train, $sign. What's the name of attendance? What's the name of attendance? I think it's called attend. This is predict attend. Why is it predict attend? What happened to our attend? Oh, here it is. Attend. Okay, so let's do attend. A-T-T-E-N-D. What's that? This is our attendance, right? Or in our training set, right? Does everyone understand? Am I talking beyond? Is it clear? Okay, but that's that one, but what's this one? What's this one? Well, let me do it. What's that? So do these have the same number of elements? This one and this one? Yeah, they both have 54 elements. Okay, so what's the difference between this one and this one? Anybody know?
One is the actual.
Yes. Which one is the actual?
The half one.
No, this is the actual one, right? The original one was this one, right? This is the actual attendance. And what's this? What's predicted by our linear model? Okay, now is our linear model necessarily going to be correct? Perfectly correct? No. So we don't expect these numbers to be the same as these. By the way, these have some decimal points in them as well. So for example, the first, this the actual attendance in the first element is what? 56,000. The predicted attendance by our model is what? 43,972. Right? Not so good, right? Well, I don't know, maybe, yeah, it's not so good. How about here, 29, what did we predict? 36, how about this, 26, 38. Okay, so we're not doing too well, right? But that's what we have. Okay, does everyone understand? Okay, so let's keep going. Okay, so we just did this one, and this one. Okay, now how about here? Evaluate the fitted model on the test set. So what does he mean by that? What are we going to do here? What's going on here? So we have built a model now. Why do I say we built a model? We just used the model to make a prediction, right? On our training set, right? We just used our model, our regression model. By the way, when I say we build a model, what I mean is we have something like this. What were the 3 variables that are included in our model? I think it was month, day of the week, month, and bobbleheads, right? So the model's going to look like this. Let me use this day of week. Okay, that stands for day of week. And let me use this month and bobbleheads. Okay? And it's a linear model. Linear means that we're not squaring, we're not doing, all right, anyway. So we're going to have a coefficient here, call it A1, plus a coefficient here, call it A2, plus a coefficient here, call it A3, and then we also have a intercept, or a constant term, call it A4. Okay? So we're building this model. We're saying, what is y? Sorry, y is attendance. Okay? We're saying that we can, and now we have coefficients. We built the model means we have these numbers, A1, A2, A3, A4. That's what R did for us. That's what the LM function did for us. It gave us a number for this, a number for this, a number for this, and a number for that. Okay, so now we have an equation that will predict attendance based on what the day of the week is, what the month of the year is, and what the and whether it's bobblehead or not. Okay, you understand? So when we fill those in, the LM function created a model which will predict the attendance. Okay, does this make sense? Okay, so that's what the LM function did. So, any questions so far? Okay, now it's a linear model, meaning we could have said, oh, I want to know a model that had that and also that. So I want to have day of the week, but I also want to include day of the week squared. Maybe I think that attendance is dependent on the square of the day of the week. I don't know why we would think that, but we might think that. And so we could check that model, but we didn't. We only included 3 variables, not these 4. We didn't include like the square of the day of the week. We could have, and there are easy ways to include all kinds of combinations of the variables in R. There's easy ways to do it. But anyway, in our case here, we only included those 3. Does everyone follow? So, is that clear so far? Any questions? Did we do this in Excel? Didn't we do a regression in Excel? in this class, or was it in my other class? Did we do it in this class or not? Regression in Excel. What? We did it, right? So you know what I'm talking about with regression, right? Okay, so we're doing that here, but here, when we did it with Excel, I think we only used one variable as an input variable, but here we've used 3, as we wrote up there. Okay, now, okay, and now we just did what? When we did this, we got this data here. So what was this again? These are what our equation, this equation predicts for attendance. It's not necessarily correct, right? It could be wrong. In fact, it is wrong. I don't think it's right even in one case, right? None of the predictions are perfect, but hopefully they're close. Okay, so what does he do next? He does what? This one. So what's this one going to do? He's using the predict function again. He's using the same model as before. But what's the data? I guess I didn't even know. There's a function called, there's a parameter called new data. And you can put this in there. So what data are we putting in now? We're predicting on our test set. Okay, so let's do that. So everybody do that. Do this one. Predict on your test set. Now, how do I see the results? How do I want to compare the actual to the predicted in the test set. I want to see both of them. The actual versus the predicted in the test set. How do I do that? We did it already for the training set. Now we can do it for the test set. How do we show it? I just want to see it on the screen. Just the way we did it before. So I want to see this one and this one, but not for the training set, but for the test set. So I just have to change this to test and this to test, right? Okay. So let's just do it just to see what it looks like. So this should be, I'll do that one first. This should be test. And then this should be train, predict, test. Okay? You see? Is this clear? All right, now here's the question. Did everyone do that? Everyone have this set here and then this set here. Okay, now here's the question. Why do we split into training and testing? Why did we do that in the first place? Why did we split our data into training and testing? What's the purpose of doing that? We went through a lot of trouble to make a training and testing set. Why did we bother to do that? No reason. Just to learn R? Just to go through a bunch of functions, like the subset function and stuff? Is that why we did it? Why did we split into training and testing? reason? You don't think it was a good idea? What's the logic or the purpose of doing that? Okay, so let's look again. So this was on the train, and we did a prediction. This was the actual results of attendance, and these are the predicted attendance, right? We saw, of course, that we didn't get the same thing here and here. But then we did it again over here. This was the actual attendance in the test set, and this was the predicted attendance in the test set. But why did I split it up? Remember, we made a model, right? The model is where we make, is how we made the predictions, right? We build a model, then we can make predictions, right? Of course, our predictions weren't perfectly accurate. The model came here, right? On what data was the model built? Find the code, find the R code, and tell me on what data was the model built. So go back to the R file and find and tell me on what data was the model built. So where did we build the model? Here. The only time we used the lm function, that's when we built the model. What data did we use to build the model? The what? The training data, right? And then we did what? At the end, the last thing we just did was we made predictions on which data set the last time we did it. On the testing data, right? So we built the model on which data? The training data, and we tested it where? On which data? On the testing data. So doesn't that make sense? Right? You don't want to build the model on the training set and test it on the training set. You want to test it on new data. Right? On data that you didn't use to build the model. You want to build the model and then say, oh, how well is it going to work later? Right? So later means on some new data. And our new data is our testing data. Because we didn't use that to build the model, right? We separated it out and we built the model only on the what? Only on the training. We built it only on the training. Okay, so that's the logic, right? We don't want to test the model on the same data that we built the model on. That doesn't really make sense. Or if we can avoid it, we don't want to do that because we want the model to be useful on new data. So we test it on new data. And that's why we went to all of this trouble to split the data into training and testing. Okay? So that's what he does. And then, I don't know, the rest of it, what is the rest of it? I'm not sure. I think he's going to make some graphs here, but we don't have time to do it. All right, but that's the main point. Oh, so the rest is he's going to evaluate. One thing he wants to do is we want to get a number for how important bobbleheads are. How much will they increase attendance? So all we want to know is, what was this coefficient? So if this coefficient was 10,000, remember bobbleheads is a 0-1 variable. Bobbleheads was a 0-1 variable. So if this coefficient was 10,000, then if this is 10,000 times 0, that means what? What the attendance is going to be when bobblehead is 0 means when we're not offering the bobblehead. And then if bobblehead is 1, that means we are offering bobblehead. What's going to happen? If A3 is equal to 10,000, what's going to happen to attendance? It's going to be increased by 10,000. So we can say, what's the effect of bobbleheads on attendance? if you offer bobbleheads, you get an increase of, for example, 10,000 people. Okay? And that's the method here that we follow in order to understand the effect of bobbleheads on attendance. Okay? So we use, in this case, a linear model, and we build the regression out, and we figure, and it tells us what this is. And then we know the effect of bobbleheads on average, right? It's not gonna work every time in the same way, but that's our estimated value of bobblehead. Okay? Okay, so we did our first data mining today, and that was kind of the hard part because we had to learn about training sets and testing sets. After that, you can just build lots of different models. You have the basic idea there. You can try different models. Okay? Okay, so that's that. I'll stop this now. And I'll post this.